morning. I welcome you all for today's discussion in the week 5 of Fluid Dynamics and Turbo Machines course. Today we will talk about the tutorials on the problems that we can do based on the lectures we have got in this week. So, essentially what we will do is we will solve some problems based on thermodynamics as well as the non-dimensional approach that we have followed in case of turbo machines. So, in the first problem we are talking about the problem of thermodynamics, where we will apply the first law of thermodynamics. The problem statement is like this: air leaves a heat exchanger and enters a turbine at a temperature of 800 degrees centigrade and at a speed of 30 meters per second. The temperature of the air at the exit of the turbine is 650 degrees centigrade and its speed is 60 meters per second. Mass flow rate of air is given as 2 kg per second. We need to calculate the power output from the turbine assuming no heat transfer. You can consider that the Cp for air is 1005 joules per kg Kelvin. You also assume for this problem the turbine to be 100% efficient. So, whenever we come across these problems, I suggest that you draw a picture like this and write down the values that are available. Like for example, we are having a flow from inlet to the outlet of the turbine. There is an expansion process. So, just make a schematic for expansion. Then we write down the inlet temperatures and velocity or pressure, whatever the information is given. In this case, temperature and velocity are given. You also note that the temperature is given in 800 degrees centigrade. Please convert into absolute scale and write it in Kelvin. And similarly, write down the quantities which are available in the outlet. And if there is pressure information also available, please write it down. In this case, we have only temperature and the velocity. So, then we can apply and we also know that there is a work done and that is given by W prime. So, when we apply the steady state steady flow energy equation for the turbine, we can write that Q prime minus W prime equal to m dot H out minus H in plus V out square minus V in square whole divided by 2 plus G multiplied by Z out minus Z in. And we know that the problem statement says that there is no heat transfer. So, for under this condition of no heat transfer, we can say that Q prime equal to 0. And we have also discussed while talking about the steady state steady flow for gas turbines and steam turbine applications, or for that matter compressors. We have talked about that the changes in potential energy can often be neglected in comparison to the other two terms and the changes. So, we will make this assumption and we will say that the changes in the potential energy is not significant. And then we can simplify this equation and write that W T prime, please recollect that we have used the notation T for turbine. W T prime is equal to m dot H in minus H out plus V in square minus V out square by 2. And we can assume that Cp is constant for air, which is given here, and then we can write that W T prime is m dot Cp T in minus T out plus V in square minus V out square whole divided by 2. And thus, when we substitute the values, we get that W T prime is 298.8 kilowatt. Please note the unit, and then if you take care of the calculations, if you have to divide the quantity that is given here by 1000, you will get this answer. So, what we learnt here is we learnt to use the straightforward application of the first law of thermodynamics with respect to the steady state steady flow. Please note that it is not mandatory that Q prime is always 0. There could be some problems, some instances where heat transfer rate is given, and in that case you have to consider it. Similarly, the case of change of potential energy. Now, we will take this problem further. We will assume that the exhaust from the turbine flows through a nozzle. It is given that the speed of the air at the exit of the nozzle is 544 meters per second. So, what do we have? We have the air coming out of the heat exchanger, flows into the turbine, and from the turbine that air enters the nozzle, and at the exit of that nozzle it is 544 meters per second. So, we will take whatever we have learned from the last example and we will start from there. We need to calculate the temperature at the exit of the nozzle, assuming no heat transfer and no friction. So, what we will get here is that we have a nozzle, again we have got a schematic of the nozzle. The flow is in this case is from right to left. We know from the previous problem that T in is given and V in is also given. At the exit, however, the T out is not given and V out is given as 544 meters per second. So, we can apply the steady state steady flow energy equation for nozzle and we can write the same equation. But here we have to take care of the fact that not only Q prime is 0 because there is no heat transfer, we also should know that since the nozzle does no work or the flow inside the nozzle does no work, then in that case W prime also goes to 0, and from our assumption we continue from the last example that the changes in the potential energy is 0 or negligible rather, and then we can get the H out minus H in is V in square minus V out square whole divided by 2, or in other words H out is equal to H in plus V in square minus V out square by whole divided by 2. Assuming the constant Cp as we have done in the last problem, we can say that T out is equal to T in plus V in square minus V out square by 2 Cp. When you are using this value of Cp here, please take care of the units, because sometimes we can say it in as 1.005 kilojoules per kg Kelvin. So, you have to convert the unit accordingly. And then when we substitute the values, we get that T out equal to 923 plus 60 square minus 544 square, both are given, divided by 2 into 1005, and this gives rise to the temperature of 504.6 degrees centigrade or 777.6 Kelvin. We can extend this problem of expansion in the turbine by now considering a more realistic case where the efficiency of the turbine is not 100%, and that we will solve in the third problem. In this problem, let us look at it more carefully. We see that air leaves a heat exchanger at a temperature of 800 degrees centigrade, the same problem statement that we have given in the first one, and enters a turbine at a speed of 30 meters per second. Speed of air at the turbine outlet is 60 meters per second. Temperature of the outlet assuming isentropic expansion is given as 650 degrees centigrade as we have given in the first problem. But this 60 meters per second corresponds to a real case, because in this case we will consider the efficiency. So, the mass flow rate of air is 2 kg per second. We need to determine the pressure ratio across the turbine. We calculate the power output from the turbine assuming no heat transfer. We also consider the statics to static efficiency of the turbine to be 80%. So, whatever the conditions have been given for the velocity corresponds to the actual case of a statics to static efficiency of 80%, and then we need to determine also the total to total efficiency of the turbine under these conditions. While solving such a problem, we should do two things. First, we should draw the layout and write down what all are given. So, we can say that at the inlet the temperature is given T, I am using the notations 2 and 1 as I have done in the graph. That is because writing in and out will be little more cumbersome in the graph. So, I am writing in for 2 and out for 1. I will give a justification in the next week's lecture why I am using such a nomenclature, because in most of the textbooks you will see that in is either given with 1 or written as in. Here I am using in with 2 and out with 1. That is because just to remind ourselves that at the inlet the pressure and temperature of the turbine of the flow inside the turbine, that is going inside the turbine, is actually higher than compared to the when compared with the flow that is leaving the turbine. So, these 2 and 1 actually reminds us about these notations. So, when we look at the process in a HS curve, which we have already done while discussing. Let us revisit this graph again. So, 2 is the point here, which is my inlet. Had it been an isentropic expansion, I would have reached the point 1 s. However, the static to static efficiency of 80%. So, we reach a point 1. The corresponding stagnation states are 02, 01 s and 01. 02 and 2 are related with this difference of the v square by 2 terms, or like in 01 s and 1 s and 01 and 1. So, please note, I am reminding you again that 2 corresponds to the inlet, 1 corresponds to the outlet. Anything with 0 at the beginning like 01, 02, 01 s etc. corresponds to the stagnation states. S denotes the isentropic expansion process for that inside the turbine. So, we have to find out the pressure ratio P 2 by P 1. While doing it, we can invoke the pressure temperature relationship. We can write the pressure ratio R is given by P 2 by P 1 and it is equal to T 2 by T 1 s whole to the power gamma by gamma minus 1. When we substitute the values, we will get that the pressure ratio is 1.69. So, P 1 is the isobar on which both 1 s and 1 lie, and since this is an isentropic process, this relationship we can use. Now, the second part of the problem says that we have a statics to static efficiency of 80%. We need to find out what is the actual work output from the turbine or actual power output from the turbine W prime. To do that, we can invoke the relationship that we have for static to static efficiency. We know that it is H 2 minus H 1, that is the actual enthalpy drop, divided by H 2 minus H 1 s, the ideal enthalpy drop, and when we substitute the values, Cp comes out because it is constant like we have done before, and then we can find out that the temperature at the outlet at 1 is 953 Kelvin. And then we can find out W prime as m dot H 2 minus H 1, which is m dot Cp T 2 minus T 1, and we get 241.2 kilowatt. Again, please note the unit. Whenever you are writing solving problems, you have to give the appropriate unit. And now next we come to the third part of the problem, which is total to total efficiency. Let us go back and look at this graph again. So, we are talking about total to total efficiency, means we have to deal with 02, 01 s and 01. None of these are given in the problem. We have to then first find out these states 02, 01 and 01 s. Let us see how we do it. So, we know that the stagnation enthalpy H 02 is nothing but H 2 plus V 2 square by 2, and then we can write that T 02 is T 2 plus V 2 square by 2 Cp. And in this case, of course, we note that the change because the kinetic energy being very small, from 1073 of the value of T 2 to T 02 is only 1073.45 Kelvin. In the same way, we can find out H 01 equal to H 1 plus V 1 square by 2, and then we can find out the T 01 is T 1 plus V 1 square by 2 Cp, which gives me 954.79 Kelvin. How do we find out the T 01 s or H 01 s? Then we have to ask ourselves that is V 1 equal to V 1 s. I go back to the curve and you can see that V 1 is square by 2 is this distance and V 1 s square by 2 is this distance. So, from the graph what does it appear? Does it appear same? If not, why? So, let us look at the reason. Is V 1 equal to V s? We ask ourselves this question and we see that it is no. Why? This is because the densities at 1 and 1 s are not same. Why it is not same? See, it is on the same isobar, so pressures are same, but is temperature same? We just now found out that the temperature at 1 that is T1 is not the same as T1s, and hence the densities will not be same. So, let us look at it. So, we are talking about the mass flow rate m dot equal to rho 1 A 1 V 1, which even in the ideal case should have been rho 1 s A 1 s V 1 s. Now, what is A 1? A 1 is the area at the exit, and V 1 is the corresponding velocity at the same location. Now, area of the turbine does not change depending on the process. Can we say that the area of the turbine will change just because the process is not isentropic? No. So, what does it mean? It means that A 1 and A 1 s are same. So, we get from this relationship that rho 1 V 1 equal to rho 1 s V 1 s, and hence since we are interested in finding out V 1 s, we can write that V 1 s is V 1 times rho 1 by rho 1 s. And now we can write density in terms of pressure and temperature, and then we can write that V 1 s is essentially V 1 multiplied by P 1 by R T 1 whole divided by P 1 by R T 1 s, and that leads to that V 1 s is V 1 multiplied by T 1 s by T 1, and we get V 1 s is slightly less than V 1. V 1 if you remember was 60 meters per second, V 1 s is 58.11 meter per second, particularly for this problem. And then we can find out T 01 s in the same way we have done earlier for T 02 and T 01, and we can get that T 01 s is equal to T 1 s plus V 1 s square by 2 C p, which gives me 924.68 Kelvin. So, we got T 01 s as 924.68 Kelvin, and then we can substitute in the relationship for eta T t, which is H 02 minus H 01, which is the drop in the stagnation enthalpy between the inlet and the actual condition at the exit, whole divided by H 02 minus H 01 s corresponding to the ideal stagnation enthalpy drop, and that gives me 79.76%. So, you learned that with the help of course, the example of turbine, how to apply these definitions of the static to static and total to total efficiencies. You can also extend these ideas to find out the other terms like pressure if it is required, because we already know pressure ratios. If in the problem any one of the pressures are given, we can find out all other pressures. That type of problem I will set it in the tutorials, and I hope that you will all able to solve it. So, this brings us to the last problem that we are going to discuss for today, and that is on dimensional analysis. The problem that I have chosen is based on the turbo machine applications, but in the tutorial that said that I have given corresponding to this week 5, we will also talk about the dimensional analysis problems related with fluid flow. Let us look at this problem. It is said that we want to make a prototype of a hydraulic turbine, which has 6 meters diameter and which will produce 55 megawatts of power when it is running at a rotational speed of 94.7 rpm under a net head of 25 meters. So, this is a turbine we want to make, and as I have said that one of the motivations for doing non-dimensional analysis is to make a model, test it and then fabricate the prototype. So, we want to make a laboratory scale model, in this case whose diameter is 300 millimeter, which will also operate under a head of 25 meters. We need to determine the rotational speed of the model turbine and the power produced by this model turbine. So, we can use the relationship connecting the specific work or GH. If you remember, I have talked about that in case of hydraulic machines like hydraulic turbines or in pumps, we often replace the specific work with a product of G and H, and so we can write that GH for the model is divided by Nm square dm square is equal to GH for the prototype divided by Np square dp square. That comes from the relationship that GH by N square d square is constant. So, then we get that Nm is nothing but Np multiplied by dp over dm, and we get that Nm is 1894 rpm, that is 20 times. And then I should have also mentioned that Hm is equal to Hp is given in the problem. Then we come to the power produced by the model turbine. We know that Pm by rho n cube d to the power 5 is constant. So, we can write Pm by rho m nm cube dm to the power 5 is equal to Pp by rho p np cube dp to the power 5, which gives me Pm equal to Pp multiplied by dm by dp whole to the power 5 multiplied by nm by np whole cube. If you substitute the values, you should get 137.5 kilowatt. This brings us to an end of the dimensional analysis. In the next week, that is week 6, we will start with the description of turbo machines, in the sense that we will talk how to represent the turbo machines in a graphically. We will talk about the velocities that are present inside the turbo machines, and we will take you through Euler's equation, and we will talk about the losses. So, with this I conclude this discussion on the tutorials with corresponding to week 5. Thank you.